In this video, we're going to wrap up our discussion of SLR parsing. We're going to give the full SLR parsing algorithm and also talk about some important improvements. The SLR parsing algorithm we discussed in the last video has one major inefficiency, and that is that most of the work that the automaton does when it reads the stack is actually redundant. And to see this, think about the stack. So we have our stack. This is the bottom over here. And this is the top of the stack over here. And what is going on at each step? At each step, we might shift something onto the stack, so we might add one symbol, or we might pop some symbols and push one symbol onto the stack. But basically, there's going to be some small number of symbols that change at the top of the stack at each step. But most of the stack stays the same. And then we rerun the automaton on the entire stack. And so this work is all repeated. Everything that stayed the same from the previous stack is repeated work, and then we do a little bit of new work just at the very top of the stack. And clearly, if we could avoid this, we could make the algorithm run much, much more quickly. The way to exploit the observation that most of the work of the automaton is repeated at each step is to simply remember the state of the automaton on each stack prefix. So we're going to change the representation of the stack. We're going to change what goes in the stack. So before we just had symbols on the stack, but now we're going to have pairs. Each element of the stack will be a pair of a symbol and a DFA state. Thus, the stack now is going to be a stack of pairs, and whereas before our stack would have consisted just of the symbols, sim1 up to simn, now we're going to have the same symbols, but each one of them is going to be paired with a DFA state, and that DFA state is going to be the result of running the DFA on all the symbols to its left, so all the symbols below it in the stack. So if I think about my stack, again, if I draw a little picture of a stack as a line, then the DFA state here, let's call this state I, will be the result of running the DFA on the entire stack contents to the left of that point. And again, if I look at some other point in the stack, at the stack state that's stored there, that would be running the result of running the DFA on the entire stack contents up to that point. And one small detail here is at the bottom of the stack we have to get started. We need to have the start state stored at the bottom of the stack, and we just store that with any dummy symbol. It doesn't matter what symbol we pick. So now we're ready to actually give the details of the parsing algorithm. And the first step is to define a table, goTo, and this maps a state and a symbol to another state. And this is just the transition function of the DFA. This is the graph of the DFA written out as an array. Our SLR parsing algorithm will have four possible moves. A shift X move will push a pair on the stack. X is a DFA state, so that's named in the shift move now. And then the other element of the pair is the current input. And then we'll also have reduce moves, which are just as before. So to recall, a reduce move will pop a number of elements from the stack equal to the length of the right-hand side, and then it will push the left-hand side onto the stack. And then finally, accept and error moves for when we've successfully parsed the input and for when the parser gets stuck. The second parsing table is the action table, which tells us which kind of move to make in every possible state. The action table is indexed by a state of the automaton and the next input symbol. And then the possible moves are things like shift, reduce, accept, or error. So let's consider when we do shifts, if the final state of the automaton at the top of the stack has an item that says it would be okay to shift an A and goTo, that is, from this state, we could go to state J on input A, then the move in state I on input A will be to shift a J onto the stack. And think about what that means for a second. What that says is that we have a stack, and then the next input is A, and that at this point, it's okay to shift an A onto the stack. And furthermore, that the state of the automaton at this point is SI. Okay, so the state of the automaton at the top of the stack is SI, the next input is A. Remember that the goTo table is the transition function of the machine. So if we move the vertical bar over, if we shift that A onto the stack, well, now we don't just put A on the stack, we have to put a pair on the stack. And the question is, what machine state should go there? Well, it's going to be the state that we would reach from state I, from state SI, on input A, which the goTo table tells us in this case is state Sj. And for that reason, the action when we terminate in state I and the next input is A is to shift the pair A comma J onto the stack. The other three moves that go into the action table are things we've already seen. So if the final state of the automaton at the top of the stack has an item that says that we can reduce and the follow condition requirement is satisfied, namely that the next input can follow the left-hand side non-terminal of the production, then in the entry I, when we're in state Si and we have input A, we can reduce by the production X goes to alpha. And there's one exception here. We're not going to do that reduction if the left-hand side is the special start symbol, the new start symbol that we add to the grammar S prime, because in that case, if the item that we're going to reduce by is S prime goes to S dot, and we're at the end of the input, then we want to accept. And any other situation is an error. So in any other situation, if we're in state I and we have the next input is A, well, we don't know whether to shift, reduce, or accept, and so that is an error state. Finally, here is the full SLR parsing algorithm. And I'm just going to walk you through it so that we can see how all of the ideas we've been discussing and all the various pieces fit together. Let's let our initial input be called I, and we'll just give it a name, and it's going to be treated as an array that we can index. The index will be called J, and initially it's 0, so that we're pointing to the first token in the input stream. We'll just assume that the first state of the DFA is called state 1, and that means our initial stack is going to have state 1 for the state of the automaton and some other dummy symbol that we don't care about in the first position. So the stack is just a pair with it says that we're in the start state of the DFA. And now we're going to repeat the following loop until we've either successfully parsed the input or we detect an error. And at each step, what are we going to do? Well, we're going to look at the next input symbol, and we're going to look at the final state of the automaton on the stack contents, and that's always the state of the pair that's on the top of the stack. And we're going to look those two things up in the action table, and that's going to tell us what kind of move to make. So let's just go through the moves in order. Let's consider the shift move first. So what happens? If it says that we're supposed to shift and go into state K, then what we're going to do is we're going to shift the input. That means we're going to take the next input symbol, or the current input symbol, excuse me, and we're going to push that onto the stack together with state K of the automaton. So that pair goes onto the stack, and we also bump the input pointer so that we're looking at the next character of input. Now, let me erase that so you can continue to read it. Now, what about the reduce moves? So this one's a little bit interesting. First thing we're going to do is we're going to pop a number of pairs off the stack that's equal to the length of the right-hand side. So we pop a number of items off the stack that's equivalent to that's equal to the right-hand side of the production. And then what do we push onto the stack? Well, we're going to push the non-terminal on the left-hand side onto the stack. And now the question is, what state goes onto the stack? What DFA state? Well, now that we've popped the stack, we can look at the new top state of the stack. So the DFA state, what is now the top state after we've done the pops, will tell us what the final state of the DFA was on what is left of the stack. And then now that we're pushing X onto the stack, we want to know what state the DFA would go into on the transition labeled X. And so we use the goto table to look that up. The current top state of the stack on symbol X, where does the DFA go? That is the state that gets pushed onto the stack. And then finally, if the move is accept, we halt normally, and if the move is error, we halt and report an error or execute our error recovery procedure. One interesting thing about this algorithm is that it uses only the DFA states and the input. The stack symbols are not used in any really interesting way. And so we could actually get rid of the stack symbols and just do parsing with the DFA states on the stack. But that, of course, would mean throwing away the program, and we still actually need the program for the later stages of the compiler. So in order to do type checking and code generation, we still need to keep the symbols around. Now, simple LR parsing is called simple for a reason, and in fact, in practice, it's a bit too simple. The widely used bottom-up parsing algorithms are based on a more powerful class of grammars called the LR grammars. And the basic difference between the LR grammars and the SLR grammars is that look ahead is built into the items. So what does that mean? Well, a LR1 item is going to be a pair which consists of a item, just like we saw before, and this means exactly the same thing as before, and a look ahead. And in the case of an LR1 item, there's just one token of look ahead. If this was an LR2 item, there could be 2 tokens of look ahead in there. And the meaning of this pair is that if we ever get around to a state where we have seen all of this production, all of the right-hand side of this production, then it's going to be okay to reduce if the look ahead at that point is $, if it's the end of the input. And of course, there could be any other token in there, any other terminal symbol in there besides $. And this turns out to be more accurate than just using follow sets. Recall that at the point where a reduction decision is made in SLR parsing, we just look at the entire follow set for the symbol on the left-hand side of the production. And this mechanism of encoding the look-ahead into the items allows us to track at a finer granularity which look-aheads are actually possible in particular production sequences. And if you look at the automaton for your parser, actually it's not an LR1 automaton, it's an LA-LR1 automaton, which is something very close to an LR automaton. It's a little bit of an optimization over a pure LR automaton. But anyway, it uses exactly the same kinds of items with this pair of a standard LR0 item and a look ahead. If you look at that automaton, you will see items that look like this, and that should help you in reading the automaton and figuring out what it is doing.